Welcome back. So we were talking about advanced training algorithms. So in particular, we talked about adaptivity and momentum as two integral components of modern optimization algorithms for deep learning. If you recall, when we talked about momentum, we also discussed this perspective of bias variance trade-off. Essentially, what we said was that compared to the estimator of the simple SGD algorithm, the momentum vector is essentially a new estimator of the true gradient, which is very costly to calculate, right? That's why we are using a stochastic algorithm such as SGD. But compared to SGD's estimator, where the estimator is unbiased and has some variance, the momentum has some bias, but lower variance than GT, the estimator of SGD. Okay, so this gives us an idea then. Is it possible to come up with better estimators that have lower variance? Okay, because if you recall, the theorem that we discussed for SGD with momentum algorithm did not show any improvement over SGD. So we want to see whether there is a principled way that we can leverage to reduce the variance, maybe also reduce the bias a little bit more, such that we provably improve upon a stochastic gradient descent. Okay, so therefore we want to spend some time talking about variance reduction. Okay, and in particular we want to answer this question: how can we get better variance reduction methods? Now, fortunately, there are a lot of elegant ideas in classical statistics, and we're going to leverage one of those ideas, notably control variates. Okay, so it's a very, very simple idea. So let's talk about it a little bit more abstractly, and then we're going to see the application to optimization as well as training of deep learning models. Okay, so let's imagine that I have this quantity capital F that I want to estimate, and I have access to this capital G, which is an unbiased estimator of F. Okay, now what I'm going to do, I'm going to, let's say, use two other estimators or two other random variables, x and y, such that expected value of x is exactly equal to expected value of y. Using these, I'm going to form a new estimator, z, which is the original unbiased estimator g plus some parameter beta times x minus y. Okay, so it's not quite clear why we want to do this, but let's discuss the bias and variance of this new estimator. Okay, so in particular, we are looking for estimators that have low bias and low variance, right? So now we want to look for conditions such that this new estimator is better than the old one. Okay, so when we say it's better, again, we are talking about the bias and variance. So let's calculate the mean and variance of z. Mean should be quite easy. By linearity of expectation, we can basically decompose this expectation in the middle as expected value of g plus beta expected value of x minus beta expected value of y. And remember our condition here, x and y have the same mean, so these two terms will cancel. And also we assume that g is an unbiased estimator of f. So this term is nothing but f, which means that z is also an unbiased estimator of f. Okay, so this is good. So using this construction, we are not incurring any excess bias. Now let's talk about the variance. So this is how we define the variance in this class for vectors. So here I'm just assuming that z is also a vector. So the variance can be written as follows. Again, it's a quadratic term. We can expand it and then use the linearity of expectation again. So it's going to have three terms. This is basically the variance of g. Okay. And there is a quadratic term here plus a cross product term. Okay. Now, this could mean that we are increasing the variance, because the second term is positive. So I have the original variance for my original estimator g. I'm adding something positive to its variance. But that's not the whole story. I have this cross product term. And this cross product term could be positive or negative, okay? So if you're looking for a better estimator, that means that it still has this unbiasedness condition, so it must have a lower variance. And it could have a lower variance compared to our original estimator G if the following condition is satisfied. Effectively, I want the sum of the second term and the third term to be negative. If that's the case, I am going to reduce the variance, okay? So this boils down to this condition that if 2 times this expectation is less than beta times basically the expected value of x minus y squared, then we may get a reduction in variance while at the same time retaining the unbiasedness condition, okay? So therefore, when people want to use this idea, they have to be careful which x, which y, and which beta they use to ensure that they don't increase the variance, rather they decrease the variance, okay? And this is exactly what we can do in optimization, okay? So in particular, let's recall our usual update, our simple update that says that you're going to go from the current solution to the next one by following the direction of an update vector times the learning rate, okay? So our original update vector in SGD was just a stochastic gradient, right? So with in SGD with momentum, it was the momentum. Here, I'm going to consider another update vector. I'm going to call it U sub t, okay? So recall our construction from control variates from the previous slide. Now, this will be my G. I'm going to set beta to be 1. This is x, and this is y. Okay, so this is exactly the same form as before, except now I'm specifying what are these variables. Okay. So x and y depend on this vector v, which I'm going to call a reference point v, or a reference solution. Okay, v. Okay. Now, what is x? X is the true gradient of my loss function at v. Okay, so this basically means that you have to go over the entire data to calculate this gradient. Okay, y is the stochastic gradient according to the batch I'm using in the current iteration, zt, evaluated at v, and also g is basically our usual stochastic gradient. The stochastic gradient according to the mini batch I'm using in iteration t, which is zt, at the current solution wt. Okay. All right. Now, we said that in the previous slide, if I want this new estimator to be unbiased, G has to be unbiased. So this is correct, okay, because we assume that we have access to a stochastic first order oracle, as we've talked about before. But also the expected value of x and y have to be the same. The only source of randomness here is zt, the mini batch I'm using. So the expected value of x, which is the true gradient at v, is basically itself. It's a deterministic quantity, okay? And the expected value of y, which is random, will be exactly the true gradient at wv. Again, assuming we have access to an unbiased stochastic oracle, which is not a bad assumption at all, okay? Okay, so therefore, this new estimator, or update vector, is also an unbiased estimator of the true gradient at wt, okay? Is unbiased estimator of the true gradient. Okay, so we have unbiasedness, but how about the variance, okay? We basically wanted some negative correlation between x minus y. So let me go back to the previous slide, okay? So we wanted, this condition is saying that I want x minus y and g to be negatively correlated, okay? And hopefully that would mean that I have reduction in variance. This is actually something that is that we can hope to happen. Why? Because of this negative sign. Okay, so if the gradient is this is a stochastic gradient, but nonetheless, if we ignore the noise, it more or less points toward the direction of increase, as we've talked about before, right? So G is pointing towards the direction of increase, minus gradient, which is basically Y, is pointing towards the direction of decrease. So intuitively, these two are actually negatively correlated. Okay, so therefore, it is not surprising to expect that we get some reduction in variance. In particular, we can precisely characterize the variance of this update. Okay, let's assume that our loss function, average loss, is L smooth, and also let's assume that the sample losses are also L smooth. Using very basic techniques, we can show that the variance of this estimator is actually something like the smoothness constant times the difference between WT and the reference point. In particular, this is saying that the closer the reference point is to our current solution, the lower the variance. Such that in the extreme case, where the reference point is exactly WT, the variance is 0. Okay? And this is not surprising at all, because that would mean that this update reduces to exactly gradient descent. So let me write it. If V is equal to WT, then UT becomes exactly the true gradient. And obviously, true gradient is an unbiased estimator of itself with 0 variance. Okay? But this is not something we can do, right? So this is exactly the reason that we resorted to SGD, okay? Because we cannot calculate the true gradient because of the high computational costs, especially in the context of deep learning optimization when you have very large scale data sets. So this leads to the least variance, but it's too costly. So we have to settle for something else. So our main idea, therefore, is that instead of setting V to be WT, meaning that you update the reference point at every iteration, you're going to do it once in a while. Okay, so after 10 iteration, 20 iteration, etc. Okay, so you're going to only update the reference point once in a while, and this means that we're going to trade some variance for computational efficiency. Okay. So this gives rise to this algorithm, a stochastic variance reduced gradient, or SVRG algorithm. So let's see what the algorithm says. Consider again our objective, which is minimizing, let's say, the average loss. So this is the loss I have in mind. It's basically a finite sum. It has a finite sum structure, something we're going to talk about it a little more later on. It's an epoch-based algorithm, because we're going to update the reference point once in a while. Here it means that we're going to update it after the end of each epoch. Okay, so you initialize your solution. You also initialize the reference point, and set the epoch counter to be 1. You have to calculate the true gradient at V1, okay, because this is something we're going to use in the upcoming epoch. Now, this is going to have order of n gradient computation, because to calculate this, I have to go and calculate the gradients with respect to all of the data points in my data set. Okay? All right. So then we're going to start the following. Okay. So for each iteration, like before, we sample a mini batch. We form our update vector, which is now slightly more complicated than, let's say, SGD. This is exactly the construction from the previous slide. And note that to calculate the update vector, compared to SGD and SGD with momentum that required 1 gradient calculation, here we need to calculate 2 gradients. Okay, 1 here, 1 here. Okay, after calculating the update vector, we update our parameter, like using our usual update. Then we're going to check whether we finished one epoch or not. And again, epoch means whether you've gone over all of the training data points once or not. If that's the case, so this condition means that we have actually just finished an epoch. If that's the case, we're going to go to the next epoch. We're going to update our reference point. And then we also need to update basically the gradient, the true gradient at the reference point. And once again, this means that you have to go over the entire data points to calculate the gradient, so order of n gradient calculations. Okay, and this is repeated after every n iteration, where n again is the number of data points. All right. So this is the algorithm, right? So let's compare the gradient the computation of this method with the methods we've talked about before. Okay. So in particular, let's see what's the total number of gradients we are calculating. Okay. If I run this method for t iterations, let's say t is some multiple of n, right? E times n. This basically means, for instance, if e is equal to 100 and n is equal to, let's say, 10 to the 6, okay? So that's the size of the data, right? So like the million data points. So t will be like 100 epochs times 10 to the 6. So I'm going to process the data points 100 times. Then it's not going to be too difficult to see that the gradient computation is going to be 3 times e times n, which is basically 3 times t. Okay. So now compare this to SGD. In SGD, in each iteration, we basically calculate only one stochastic gradient. So in SGD, after t iterations, we have calculated t stochastic gradients. For SVRG, 3 times t. So it's 3 times as much as SGD. But order-wise, it is the same order as a stochastic gradient descent. All right. Now let's see whether this is actually better than a stochastic gradient descent and gradient descent algorithms, provably or not. Okay. So these two are something we actually showed in the class. That we discussed the oracle complexity of gradient descent, meaning that the total number of gradients we have to calculate to find a stationary point was n divided by epsilon. That is because we have to run the method for order of 1 over epsilon iterations, and in each iteration we are calculating n gradients. So order-wise is n over epsilon. For SGD, we discussed that this is basically O of 1 over O of 1 over epsilon squared, because we have to run SGD for 1 over epsilon squared iterations, and in each iteration we are calculating only, let's say, 1 stochastic gradient. Okay, so it is independent of n, as opposed to GD. It turns out that you can state an oracle complexity result for SVRG, which is something that you can refer to in, by reading one of the suggested reading materials. But nonetheless, the oracle complexity of SVRG can be shown to be something like this. So it's n plus n to the power of 2 over 3 divided by epsilon. Okay. So note that the first term is actually independent of epsilon. And this is indicating that you have to calculate basically the reference point, right? At least once. So you have to calculate the gradient and the reference point at least once. And that requires order of n calculations, as we talked about in the previous slide. All right. Now let's consider these results. In particular, I want to basically see if I want to find if I set a predefined target accuracy of epsilon, okay, which of these is better? Okay, which of these can find an epsilon solution with fewer gradient calculations? Okay. So let's first compare SVRG and gradient descent. So SVRG is better than gradient descent if its oracle complexity is lower than the oracle complexity of gradient descent. So using some manipulation, you can show that this is equivalent to saying I want epsilon to the power of 1 minus 2 to be larger than 1. Okay, and this is almost always the case, right? Because epsilon is a very small number, let's say 0.1. So 1 over epsilon squared is like 100. Okay, so 100 is always larger than 1. So what that means is that if you have a loss function which has this finite sum structure, you can go ahead and run SVRG, and it's provably better than gradient descent, no question asked. Okay, so there is no point in running gradient descent, okay, because you have this algorithm which is provably better. All right, now let's compare. Okay, so let's compare gradient descent with stochastic gradient descent. This is a comparison we've done before, but let's repeat it again. So, let's compare SGD with gradient descent. SGD is better if its oracle complexity is less than the oracle complexity of gradient descent. So again, some rearranging shows that the condition is n has to be larger than 1 over epsilon squared. Okay, and this is almost always the case in deep learning, right? Because we have these very large scale data sets. Okay, and if I set even a very low target accuracy, like 0.01, as long as I have 10,000 or more samples, SGD is better. Okay, that's the reason that we actually run SGD, right, in the first place, when we are talking about large scale optimization problems such as optimizing deep learning models. Okay. Now the big question: how about SVRG and SGD? Okay. So SVRG is better than SGD again if its oracle complexity is less than the oracle complexity of SGD. After some manipulations, again, you can basically need this condition. You need this condition to be satisfied such that SVRG is better. Okay. And unfortunately, this is almost never the case in practice. So this says that your you cannot be too accurate, or equivalently, your data should not be too large. Okay, the size of the data should not be too large. Okay, so this is one shortcoming of this very elegant idea and very elegant algorithm, right? And this is partly the reason that we, despite its elegance, we are not using it in the context of deep learning optimization. But there are other shortcomings of this method that we're going to talk about in the next lecture. I'll see you there.